Alright folks, so in this lesson I'm going to go over what a heating degree day is, how we calculate it, and then how we use heating degree days to calculate the heat lost or gained through a surface or a number of surfaces throughout the year. So let's review some of the heat loss concepts real quickly. This is an identical slide from before. Remember, we're dealing a lot with the building envelope, which is the area of a building that encloses the conditioned space. So it's usually you can find it where the insulation is, but it also could be where the floor is. It's not always easy, but just remember that's really what we're concerned with, because all of the space inside of the envelope is the area that we're actively heating and cooling, and so that's what we'll use to calculate our heating load and cooling load when we get to that. Remember that U value or U factor, it's just a property of the material. Everything has a U value. And U value is a transmittance or transmission, and so higher U means more transmittance or more transmission. So we want a smaller U overall. Okay, so things with like a lot of insulation have a low U value. R value is the inverse of U, so high R is better. R is a measure of resistance. Remember that you can add R's, you cannot add U's, and we went over that before. Very, very important that heat always flows from areas of higher to lower temperature. And then when we talked about heat flowing through a surface, it increases. So heat flow, all else being equal, is going to increase with increased surface area, increased time, increased delta T or temperature difference on either side, and increased U value. This should all be pretty intuitive if you really think about it. And then finally, the formula for heat movement is that the BTUs per hour is equal to UA delta T. So the U factor, or U value, times the area in square feet times the temperature difference on either side. And if you look at that form, if you ever forget all this stuff here with like, is it more or less temperature or more or less area, the formula is really helpful, right? Because this is heat loss. And so if I want this to go up, U goes up, this goes up. A goes up, this goes up. Delta T goes up, this goes up. Right? So it all should make sense if you look at the formula. Okay, so this is again a review, so I'm going to go over this quickly. So if I have these three surfaces, right, so I have R 3.5, R 2.5, and R1 all stacked on top of each other, what's the total R value? To do that, you just add them up. Okay, that's it. So it's R7. And then if I want to figure out the U value or U factor, I just take the inverse, 1 over 7, boom, 0.143 BTUs per square foot per degree Fahrenheit per hour. So remember, a U factor is how many BTUs will travel through a square foot of surface, if there's 1 degree temperature difference over the course of 1 hour. So that's where that unit comes from. Okay, so let's use this as a reminder of as a basis of our heat load calculation. And again, this is a review, so I'm going to go over this quickly. So remember, if we want to calculate the heat loss through a surface or heat movement through a surface, we use UA delta T. And so if we have that same, and you can feel free to pause and look this over, this is from a previous presentation, so I'm going to go quickly. If I have a U factor of 0.143, 100 square feet, 10 degree temperature difference is just those three together, UA delta T, 0.143 times 100 square feet times 10 degrees. There it is. If I increase to 20 degree delta T, you can see my U goes up. If I increase 20 degree and increase the surface area, then my BTU per hour goes up. So again, heat transmission is going to increase with increased U, increased area, increased delta T. Okay, so let's get into the new stuff. That's all review. So heating degree days. Heating degree days, or HDD, they're used to help calculate heating needs for a building. And they're an indication of the general average outdoor temperature below a certain comfortable indoor temperature. So basically, more heating degree days means more heat needed. More heating degree days means more heat needed. So it means it's colder. It's an indication of climate. And so just to give you a heads up on the way this works, for residential buildings, what we assume is that even though normally we want it about 70 degrees inside, however, we don't assume that we actually need to heat the building up to 70 degrees to make it comfortable. Why is that? Well, if we heat it up to 65, if you remember from a previous presentation, there's all these internal heat loads inside the building. You have people, people are cooking, they're taking showers, there's electronics, there's lights, pets, whatever. So there's a bunch of things inside of a house that have waste heat and cause the house to warm up. Therefore, we really only have to heat the house up to about 65 degrees. And that may change depending on what's going on in the building, the number of people, and so forth. But that's the rule of thumb that is used industry-wide residential. Commercial buildings, it turns out, that may not be an accurate statement. We'll talk about that a little more later. That's something called a balance point. But regardless, the heating degree days use this reference point. And so a heating degree day indicates, or a heating degree day occurs when the temperature drops below that point. Okay, so for a residential building, if it drops below 65, there's technically some heating degree days, which means it's implied that you need a little bit of heating. Okay, and that temperature is called the base temperature. All right, and so let's look at this map. Here's a map of heating degree days across the country, and you can see it matches up perfectly with climate zones. And the further north you go, the more heating degree days you need. So let's look at these two areas, right? So we have southern Florida down here, and then northern Minnesota, which is up here, right? So southern Florida, if you look at the map, is less than 1,000 HDD. Northern Minnesota is the white area that's greater than 9,000. So you can see big difference in climate, big difference in the HDD, right? About 9 times HDD. So what that implies is that if you have a house or a building in Minnesota and that same building in Florida, you're going to need about 9 times the heating energy to keep that house warm throughout the year. Okay, so again, more HDD means more heating needed. And how do you calculate it? It's actually really simple if you take the average temperature. So if it's colder than your base temp, right? So if it's colder than 65 for residential, all you do is you subtract the average temperature from the base temperature. Okay? And I'll go over an example here. If it's warmer on average that day, like as I said here, it's probably been about 72 degrees as I'm recording this, so it's the average temperature here was higher than my base temperature today, and there's 0 HDD on a day when it's warmer than the base temperature. Why is that? Well, if it's warmer outside than it is inside, then the temperature you need to heat it to, you obviously don't need any heating. And HDD is a measure of how much heating you need, so if you don't need heating, you have no HDD. So let's go over quick examples. So the average temperature, it's a pretty, kind of a chilly winter day, 40 degrees Fahrenheit outside. Okay, we're using our base temp of 65. What's the HDD that day? So remember, if it's below HDD, subtract it. Or excuse me, if it's below base temp, subtract it. So 65 minus 40 is 25. That's it. So there's 25 HDD on this day if it was 40 degrees outside. It's really that simple. Now you can go, usually they'll go hour to hour, but this will give you the same answer. Okay, what if the average temperature is 85 degrees outside? How many HDD do we have? Well, of course, we're above our base temp, so we don't need heating, which means we have no HDD. And that's really how you do it. And then the HDD, you just total up all of these daily HDDs and you add them up through the season, and that's your total HDD. And here's a good illustration of that. So these are actual data points from Wilmington, Delaware in 2017. This is real temperature data. And it shows you how many HDD there were each month. And you can see it was high in January, and it sort of slowly dropped, went back up in March, but lower than January, and then it dropped in the summer. Makes sense, right? It's much warmer in the summer, so it dropped, and then it goes back up in the fall and winter. Okay, and then if you want the total HDD for the year, you just add all of these up, and that's how you get it. And that's how this map was generated. It took all of those different days and added them up for an entire year, and then you put it on a map, and that tells you the HDD. Okay, so that's how you generate a HDD. Then, why do we care? What do we use it for? Well, we care because it gives us an indication of the general climate and how much heating we need. But more importantly, it allows us to calculate the approximate annual heating needs for a building. given a couple other factors. And so we can use this equation, which you'll see is very similar to our heat load calculation. Remember, our heat load was UA delta T. This is UA HDD times 24. UA HDD times 24. Okay. You can also use it to calculate CDD, just so you know, or the total cooling needs for a building. So all of this applies for CDD, or excuse me, for cooling. Okay. So let's do a couple examples. So remember that wall that was at a U value of 0.143. So if we had a 10 by 50 wall in Boston, or 10 feet by 50 feet wall in Boston, with that U factor, with an HDD of 4,500, what's the annual heating need? We just plug it in. U times U, 0.143, times the area, 500 square feet, times the HDD, 4,500, times 24, gives us 7.72 times 10 to the 6 BTU, which is about 7.72 MMBTU. Okay, so that would be the total heating needs based on the heat loss through that surface. Okay, so what if we double the R value, which cuts the U value in half? Okay, well, let's just have our new U value, 0.0175, which is half of this, times the 500 square feet, times the 4,500 degree days, times 24, and it's cut in half. So you can see that the heat loss, or the heating needs, were cut in half by doubling the insulation value, which, again, if you look at the formula, should make sense, right? Because if that's proportional to U, and if you cut U in half, that means the Q, or the heating need, is going to go down. All right, so that's one wall. What if we have 4 walls? So now we have 4 times the area. So we just take that same U times 2,000 square feet times 4,500 times 24, and we get 15.4 MMBTU. So this was one wall, and we just have 4 walls. We have 4 times the heat loss and 4 times the heating needs. So let's look at what if you have the same as the first, the second scenario here in Orlando, right? So we have 0.0715. We have 500 square foot wall. We have 550 degree days instead of the 4,500, okay? And then the same 24. So you do multiply that out and you get 0.47. So compare 3.86 to 0.47. That should make sense. If you live in Florida, you need much less heat throughout the course of a year, and that would be how you could calculate it based on, again, these assumptions. And so if you chart this, oh yeah, so very similar to the first equation. So heat transmission is going to increase with increased U, increased area, and increased HDD. Again, this should make intuitive sense. Increased U means less insulation, which is going to mean more heat flow. Increased area, which means more heat can flow through the walls. So that's increased heat loss. And then increased HDD, which means it's colder, means you're going to have a lower average temperature, which means you're going to have more heat leaving the building. Okay? And so if you compare, just if you run the numbers and you compare Boston and Orlando at these different values, you can see that Orlando, just by virtue of being in a warmer climate, is going to have, close to 10 times less heating no matter any way you slice it. So if you take the same building and you put it in Orlando, you're going to need about 10 times less heating energy. And just for illustration purposes, if you calculate the CDD, it's going to be the opposite, right? Because Orlando has much more, so cooling degree days, which we'll just touch on but not really get into in too much detail. Orlando needs a lot more cooling, and so it has much higher CDD than Boston does, right? Which means your cooling load is going to be much higher in Orlando. So there's a give and take here, right? So if you need less heating, you're going to need more cooling, and vice versa. Okay, so to review all of this, remember that HDD is a measure of how much heating is needed in a given area, and it's relative to a base temperature. Okay, and it's a proxy measure of climate. More HDD means more heating needed, which means it's a colder climate. We calculate HDD by taking the average temperature over the course of a day and subtracting it from the base temperature, which for residential we use 65, for commercial we can use different numbers. But that will be our HDD for the day, and then you take all the HDDs, just add them up every day, and that gives you your total HDD for the month or the year. Our heat loss, our annual heat loss equation is UA HDD times 24, and heating needs increase with increased U, increased area, and increased HDD. Okay, so now you know what a heating degree is, how they're calculated, and how they're used to calculate the heat loss or gain through a surface.